The Global Meteor Network. Hi everybody, I'm Mirjana Malarić from Zagreb, Croatia. I work in High School Jelkovec, a vocational school for computer science and electronics. I'm graduated electrical engineer from the University of Zagreb, and I have worked for a long time as a teacher in the fields of electronics and computer hardware. Astronomy has been a hobby of mine since I was a teenager, so I brought together my profession and my hobby. Besides visual and telescopic observations of celestial objects for students, my students and I work on projects in electronics for observing celestial phenomena. One of these projects is an Arduino Uno-driven radiometer. We also joined the Global Meteor Network, formerly the Croatian Meteor Network. I'll explain to you what the Global Meteor Network is and how could you involve your students or anyone else in this project. Recently we had an opportunity to observe the most popular shower of shooting stars in the northern hemisphere, called the Perseids. You are seeing two examples from our GMN stations. But let me first explain some basic terms, just in case. A meteoroid is an interplanetary object with size from micrometers to several meters. When this object intersects with Earth and enters the atmosphere, it causes a meteor. If the meteoroid is big enough and slow enough, it can leave a meteorite, a rock fallen to the ground that we can find and recover. Where do meteoroids come from? There are two possible sources, asteroids and comets. Asteroids are big rocks, mostly in orbit between Mars and Jupiter. During collisions, asteroids crumble. These pieces can be ejected from orbit and some of them reach Earth's atmosphere. These larger pieces of rock cause a very bright meteor called fireball when they enter the atmosphere. Comets have trails that produce lots of small pieces, a cloud of space dust called a meteoroid stream. If a lot of meteors can be noticed coming from the same spot in the sky during a period of time, we call that event a meteor shower. A meteor shower produces centimeter to millimeter sized particles which have not evolved dynamically far from the orbit of their parent body. For example, the parent body for the Perseids is comet Swift-Tuttle. Why do we care? These tiny fragments can offer us a unique view on the solar system formation and evolution. Knowing more about these tiny pieces of space dust helps us in analyzing meteor showers, sporadic meteors and fireballs, as well as increasing our knowledge of the risk to Earth from larger debris. We can predict meteoroid impact risk on spacecrafts, especially satellites, or during spacewalks. Comets containing ingredients for life, for example, Rosetta comet. Why do we need Global Meteor Network? Meteors are very local objects since they come from a height of around 100 kilometers from Earth's surface. So if we want reliable results, we need lots of observers all around the world. A solution is to have cameras acting as one big instrument connected in a network. Existing regional video networks either have expensive camera systems, collect their data in incompatible forms, or the data are distributed after a year or so. The solution to this is multinational large-scale citizen science project, the Global Meteor Network. The broad goal of GMN is to greatly expand the atmospheric coverage of video networks to a global scale, permitting continuous optical observations of meteors using a fully open source software and data model. A major motivator for the establishment of the Global Meteor Network project is to build a distributed meteor network which is treated as a fully automated decentralized science instrument. The scientific goals of the project are the following: providing the meteor community with a real-time awareness of the near-Earth meteoroid environment for publishing orbits of all observed meteors from all around the globe every morning. Observing meteor showers, computing their flux, mass indices and orbits to constrain meteor shower prediction models. Observing meteorite producing fireballs to increase the number of meteorites with known orbits and help constrain meteorite source regions. The system we are setting up runs on Raspberry Pi and uses a cheap security camera module. The total cost of parts for one meteor station is around $200. The parts needed are a Raspberry Pi 3x+ or 4 computer with a case, fan and power supply, a 128 GB class 10 micro SD card, and one IMX291 bare bones camera module with power cable and 5 volts power supply. It uses various lenses, 3.6 mm with bigger field of view, 5 or 5.6 mm or 8 mm, which is suitable for cities, or 16 mm with the smallest field of view for high precision trajectories. A security camera housing and a mounting brackets, then 2 PoE injector cables and 1 Ethernet cable. You can also buy a plug-and-play system at our private industry partner IstraStream for $400. Take a short look at the parts. The system uses transparent and open source Raspberry Pi meteor station software. It is available on GitHub. Data are automatically uploaded to the global database, where it is combined with data from other cameras to work out the orbit and often the origin of a meteor. It may even be used to work out where a meteorite might have landed. The data are used to monitor meteor shower rates and duration, accurately forecast the peak of the shower, as well as monitoring and predicting outburst and plotting the radiant, the point at which the shower appears to originate as seen from Earth. These systems help tracking minor meteor showers, sporadic meteors, fireballs, and new showers. Once a camera is set up, it all happens automatically, but you can do your own analysis of data as well. All trajectory and orbit data are free and available within 24 hours after observation. Here are some examples of the data we got. Upper left, a very dark place on the Canary Islands, La Palma. Upper right, one meteorite dropper in Canada where you can see a few fragmentations. Lower left, if there is a very active meteor shower, you can have more than 1,000 meteors in one night per camera. Lower right, finally, an all-sky camera which is not used usually for trajectory purposes because of its low resolution. And some data from our RMS camera. Despite city light pollution levels, a couple of nice meteors with 2 fragmentations are obvious. Down, a meteor shower in May named Lyrids and a meteor shower in January named Quadrantids. You'll notice a trace of beds and trace of an iridium satellite, which is communication satellite. We put a lot of emphasis on calibration methods. With 3.6 mm lenses, you get 1 arc minute of astrometric precision. Cameras are recalibrated every 10 seconds due to camera movements caused by thermal effects or wind blasts. Photometric calibration is also needed due to changes in the sky conditions. Global Meteor Network started at 1820. We now have 500 stations in 30 countries. Here is a current coverage of networks at 100 kilometers in Europe and North America. Radians shown on the slide and daily plots are available on the website. The little bright spots are individual meteor showers. The GMN observes all meteor showers that are of interest from the spacecraft impact hazard perspective, i.e. those showers which are so active that NASA monitors them and issue warnings to the satellite operators if a shower is experiencing an outburst of activity. You can scan this QR code and you'll be directed to the GMN website. The GMN project opened the development of software to contributors from the general public as a citizen science project. Students or teachers are welcome to participate. Here you can see a map of the fireball trajectory observed by 4 GMN stations. This is an example of the application of GMN data. We examine a bright fireball lasting 6.2 seconds observed above southern Croatia. Meteorite fell weighted around 100 grams. When we calculate the location of meteorite fall, students and teachers can participate in the search and hopefully recover it. Students can build their own camera system. Instructions are available at website. We would also like to have students and teachers who would take care of the educational components of the project. Perhaps we could have an international group of student specialists who can perform things like data analysis and reduction. And you'll have support from the Global Meteor Network community at groups.io. GMN cameras can be also used for other projects like variable stars photometry and sprites observations. These are upper atmospheric optical phenomena associated with thunderstorms. Here is the meteor trajectory viewer and meteor map. You can notice stations, blue dots, and fields of view of cameras. Europe and North America are well covered, but we need more cameras in the southern hemisphere. Africa, South and Central America, Australasia, Oceania. The data collected by GMN was used as a basis for several academic publications, including the scientists at the NASA Meteoroid Environment Office. I invite you to join the Global Meteor Network by visiting the website. Thank you for your attention, and if you have questions, I'm here now.